Imagine you have 5 letters that need to go into 4 mailboxes. Maybe you're distributing them randomly. Maybe you have some elaborate system. It doesn't matter. No matter what you do, at least one of those mailboxes is getting 2 or more letters. You can't avoid it. There's no clever trick, no rearrangement, no hack. 5 things, 4 containers. Some container has to double up. And if that sounds painfully obvious to you, good, it should. That's actually what makes it so powerful, because this trivial little observation, so trivial you'd feel embarrassed calling it a theorem, turns out to be the engine behind some genuinely deep and surprising results in mathematics. The formal name is the pigeonhole principle, and the classical statement goes like this: if you have n plus 1 pigeons and only n pigeonholes, at least one hole contains at least 2 pigeons. The proof is almost insultingly short. Suppose, for the sake of contradiction, that every hole contains at most 1 pigeon, then the total number of pigeons is at most n, but we started with n plus 1 pigeons, contradiction, done. That's it, that's the whole proof. Now you might be thinking, okay fine, but how does something this obvious lead anywhere interesting? And that's exactly the right question, because the art of the pigeonhole principle is never in the principle itself, it's in figuring out what the pigeons are and what the holes are. That choice, that creative act of deciding what to count and where to put it, is where all the magic happens. Let me show you what I mean. Here's the most famous warm-up. How many people do you need in a room to guarantee that at least 2 of them share a birthday? Ignore leap years, so there are 365 possible birthdays. The birthdays are the holes, the people are the pigeons. You need 366 people to be absolutely certain. With 365, it's conceivable, wildly unlikely, but conceivable, that everyone has a distinct birthday. Add one more person and you've forced a collision. 366, that's a clean, satisfying answer, and it falls right out of the principle. But here's where things start to get genuinely surprising. Take any irrational number, let's say the square root of 2, which is about 1.41421, and change. I want to show you that there are infinitely many fractions p over q, such that the absolute difference between the square root of 2 and p over q is less than 1 over q squared. Not just within 1 over q, which would be easy, but within 1 over q squared. That's a much tighter tolerance, and the fact that you can always achieve it for any irrational number, not just the square root of 2, is a theorem due to Dirichlet from 1842. So how does Pigeonhole get you there? Here's the setup. Pick a positive integer q, and consider the q plus 1 numbers you get by taking k times the square root of 2 for k equals 0, 1, 2, all the way up to q, that's q plus 1 values. Now take just the fractional parts of those numbers, the part after the decimal point. Each fractional part lives somewhere in the interval from 0 to 1. Divide that interval into q equals subintervals, each of width 1 over q. You've got q plus 1 fractional parts, q subintervals. Pigeonhole, 2 of those fractional parts must land in the same subinterval. What does that buy us? It means there exist 2 integers j and k, both between 0 and q, with j less than k, such that the fractional parts of j times root 2 and k times root 2 differ by less than 1 over q. If you unwind what that means, and this is the beautiful part, set q equal to k minus j, which is a positive integer at most q, and let p be the nearest integer to q times the square root of 2. The fact that those 2 fractional parts were in the same subinterval tells you that the absolute value of the square root of 2 minus p over q is less than 1 over q times q. Since q is at least q, that denominator is at least q squared, so the absolute difference is less than 1 over q squared. And because q is arbitrary, you can do this for every q, producing infinitely many such approximations, each one tighter than the last. All of that from Pigeonhole. The pigeons were fractional parts, the holes were subintervals, and the payoff was a foundational result in number theory. Now let me show you one more, and this one might be my favorite. Write down any sequence of 10 distinct real numbers, just any 10 numbers in a row. I claim that hiding inside that sequence, there's either an increasing subsequence of length 4 or a decreasing subsequence of length 4. You can't avoid it. No matter how cleverly you arrange those 10 numbers, one of those 2 patterns must appear. This is a special case of the Erdős-Szekeres theorem, and the general statement says that any sequence of more than r times s distinct numbers must contain either an increasing subsequence of length r plus 1 or a decreasing subsequence of length s plus 1. For our case, r and s are both 3, so r times s is 9, meaning any sequence of 10 or more numbers is forced to have a monotone subsequence of length 4. Here's the pigeonhole argument. For each element in the sequence, assign it a pair of numbers, the length of the longest increasing subsequence starting at that element, and the length of the longest decreasing subsequence starting at that element. Now, if neither type of subsequence ever reaches length 4, then each of those values is at most 3. That means each element gets assigned a pair drawn from the set 1, 2, 3 crossed with 1, 2, 3, which gives 9 possible pairs. But we have 10 elements, pigeonhole. 2 elements share the same pair. And here's the kicker, that's actually impossible. If 2 elements share the same pair, one of them comes earlier in the sequence. If the earlier element is smaller than the later one, the earlier element can start an increasing subsequence that includes the later element's entire increasing subsequence, giving the earlier element a strictly longer, longest increasing value than the later one, contradicting that they share the same value. If the earlier one is larger, you can make the same argument with decreasing subsequences instead. Either way, contradiction. So our assumption was wrong. Some monotone subsequence must reach length 4. The pigeons were elements of the sequence, the holes were pairs of integers, and the conclusion was a result that feels like it shouldn't be true. That structure is unavoidable, even in apparent disorder. Now there's a natural generalization worth mentioning, because it comes up constantly. If you have more than k times n objects placed into n containers, some container must hold at least k plus 1 objects. You can see the original principle as the special case where k equals 1, but the generalized version lets you guarantee not just a pair, but a triple, or a quadruple, or whatever threshold you need. This is the version that shows up in computer science all the time, in hashing for instance, where you're mapping a large universe of possible keys into a fixed size table, and collisions aren't just likely, they're mathematically inevitable once your data exceeds the table size. And I think what's remarkable about all of this is the contrast between the sophistication of the conclusions and the simplicity of the tool. Dirichlet's approximation theorem is a real theorem in number theory. The Erdős-Szekeres result is a cornerstone of combinatorics. Both of them follow from an observation that a child could understand. If you have more things than places, something has to share. So go back to those 5 letters and 4 mailboxes from the beginning. That image feels different now, doesn't it? Because it's the same principle, the exact same logic, that forces irrational numbers to have beautiful rational approximations, that guarantees hidden patterns and arbitrary sequences, that makes hash collisions inescapable. The obvious, it turns out, is quietly running the show behind some of the deepest ideas in mathematics. And the only real skill, the part that requires genuine creativity, is learning to see where the pigeons are hiding.